Hi, and welcome to Module 2 of Lecture 9. In the previous module, we gave you the sort of broad strokes of what continuous distributions were. Here we're going to go through and do some nuts and bolts. Now, I said last time, the major difference between continuous and discrete distributions is that for discrete distributions, you can define a probability mass function that equals the probability that any particular random variable x, remember capital letters correspond to random variables, lowercase letters to values, and a particular random variable x equals some value x. You cannot, and because of that, the probability mass function is going to be a real probability and be in somewhere between 0 and 1, and 0 means there's no chance of drawing a number, a particular value, and 1 means the chance of drawing that value is unity. You can always draw that value. That's not the case for probability distribution functions, which are the continuous analog to probability mass functions. Instead of being the probability of drawing a particular value, they're the relative likelihood of drawing this value. In many ways, they're similar to a histogram. Remember, if you recall, a histogram showed you the relative frequencies of each particular value you could draw. If you take those bars on a histogram and make them smaller and smaller together, right? So you shrink the width over and over again, you get more and more bars in the histogram, it kind of smooths it out. That will become a continuous distribution in the limit, and those relative frequencies are pretty much what we're looking at here, right? They're the relative chances of drawing any particular value. Okay. Instead, what we're going to do is figure out a way to represent these relative likelihoods. Formally, turns out part of it is easy. It's going to be the PDF is another function of the random variable that's going to give you the relative likelihoods. The difference is, to connect it to probabilities, it takes a little more effort. Instead, because we can't actually define, as I mentioned in the last module, the probability of getting a particular value, instead we get the probability of being in some range, in some region. So it's really the probability that the random variable x is in some region B. This B is a general. If it could be, depends what the actual random variable is, a random variable of. We'll be more specific in a second. But this thing is going to equal the integral of the PDF. We call this is the formula for integration. And I said last time, if you haven't gone through integration yet or don't know integrals, go back to the previous part of the class, go through the lecture on integration, and if you need to, differentiation before that, because you can't understand continuous distributions without understanding integration. So you should go back and do that first, if you haven't already. Assuming you have, we'll continue. It's the integral of the probability distribution function. The dx there helps you do the integral, tells you the variable of integration. And the bounds of the integral, because it's a definite integral, are going to be given by b. B is just some domain that is the support of the distribution. In most concrete examples we're going to do, this will actually be just a segment of the real line. So we'll instead do this and say from A to B, so it's some line segment, and that's going to equal the integral from A to B of f of x dx. And this thing is going to tell you the probability of having the random variable x having a value from that random variable drawn that's between A and B. This thing's a probability, so this thing is between 0 and 1. And the integral of the PDF between any 2 points in the support of the distribution will give you a value between 0 and 1. It must, because it's a probability. However, the PDF itself does not have to be between 0 and 1 anymore. Instead, it is between 0 and infinity. So it's always non-negative. You can have a negative probability. And a 0 probability still means you can't draw that value. However, in other words, it means that value is not in the support of the distribution. However, it can be as big as it wants to be, because all it's representing are relative values. So that is the PDF, and that's the sort of general formulas around the PDF. But that's all it is. If you get past the fact that the PDF is not an explicit probability by itself, but you must integrate the PDF over the range you care about to get the probability of being in that range, you'll be fine for the rest of this lecture. That's the only difference between discrete distributions and continuous distributions, is that. And in fact, so that's the PDF. In fact, moving to the CDF is even easier. If you recall, in the case of discrete distributions, the CDF was going to be equal to the sum of the PDF, right, of the PMF over all xi, right? So CDF, which we'll call here f of x, over all xi, all values of all the values that it takes, all discrete values, less than or equal to some value x. For the continuous case, it's an exact analog of this, just moving from the sum to an integral. So the CDF for a continuous distribution, again, capital F, is going to equal the integral from negative infinity to x. So we're taking this, effectively the sum, right? We're integrating from everything from the very back of the integral, to the very back of the domain, right? Negative infinity is the smallest you can possibly get in this one dimension, all the way to the point x we care about. And you're going to integrate the PDF over that range, over those bounds. This is a very close analog, as you can see, between the discrete and the continuous cases. And the meaning of the CDF is the same. It's the probability that the random variable x is less than or equal to some value x. We made the same exact thing for both discrete distributions and continuous distributions. There's no difference at all. And in fact, if you've noticed, that this is the same thing as saying the probability that capital X is in the range from negative infinity to x. This is a closed bracket. So in fact, we have the exact same meaning as we had for any region A to B. Whenever you're trying to compute the probability that the random variable x is in some region, you do the same thing. You integrate the PDF over that region. Doesn't matter if it's a PDF. Doesn't matter what you're trying to do. If you're trying to just figure out the area in a particular region, the probability in a particular region, or the probability less than or equal to x. Doesn't matter what you're doing. You do the same way every time. You integrate the PDF over the required bounds, whether it be from A to B or from negative infinity to x. There's no difference. And I should actually say, this up here I did was sloppy. You never integrate over something that is in the bounds. So this integral should actually be over some x prime, some different dummy variable, or I could use z, f of z, dz. It doesn't matter. It doesn't matter what the letters in here are, but I shouldn't use the same letters as we have in the bounds. If I'm integrating to x, I should not use x in the integral. So that was sloppy, but actually it's good that I did this because it gave me an opportunity to make sure that was clear. Again, okay. So that's the CDF. It means the exact same thing as it did in the discrete case. No difference at all. It's the chance of drawing a value less than or equal to some value of x. And just like before, the CDF, because it is a probability, is between 0 and 1. And if I want the probability of being greater than that value, then it's 1 minus the probability of being less than that value, because you can either be less than the value or greater. So again, the probability of being, right down here, probability of being greater than some value x is equal to 1 minus the probability of being less than that value, which is 1 minus f of x, which will come up sometimes. So, and all the stuff we did for the CDF, it still holds. There's nothing different at all, except you move a sum to an integral. So that's most of what we're going to talk about in this module. The last topic to mention briefly is our parameters of PDFs and CDFs. In general, they're the same as for discrete distributions. You can have means, you can have standard deviations or variances. Recall these were location and scale parameters we talked about. A third kind of parameter that comes up a bunch in continuous distributions is the shape parameter. Right? Let's write shape. Right, so we have location, scale, and shape. We've talked about location and scale. Location shifts the mean effectively of the distribution. Scale changes how spread out it is, the dispersion, the variance. Shape changes but neither of those actually change the real shape of the distribution. It stays pretty much how it is. A shape parameter changes the actual shape of the distribution, and you can get pretty different shape distributions. As I said in the previous lecture, I'm not going to draw these things out because I'm going to do a bad job of it. So instead, I'm going to really quick show you a picture from the book. These are different values of the beta distribution. The beta distribution has two parameters, alpha and beta. And as you can see here, they have very different shapes depending on the values of alpha and beta. Sometimes you have things like this. There's kind of like an exponential distribution. Sometimes there are humps. Sometimes it goes up like this and down. So it looks like an inverted U. That's a regular U. It looks like a U. The beta can be very different depending on the two shape parameters, alpha and beta. The beta, by the way, is useful occasionally, although not often, because it has limits between 0 and 1. So you see it sometimes in Bayesian analysis and Bayesian stats. Okay. So that's most of what we're talking about here. Just a brief word before I finish on why we're going through this. You might be sitting here going, okay, but you know what? I wasn't really looking forward to seeing integrals again. So why do I have to do this? Aren't most things in political science discrete? Right? We count bills, we count wars, we count people, we count votes. These are all discrete things. Why do we have to do continuous values? Well, it turns out there are lots of things we end up using in political science and social sciences in general that use continuous distributions. The biggest one is as disturbances in our error term, as the error term in our statistics, in our linear models. If you recall, before we discussed a linear model with one variable looked like this. So we have a dependent variable, an independent variable, some coefficient that tells you how changes in the independent variable affect the dependent variable, plus some error. We did this example at length a little bit at the end of the lecture on optimization, one dimension. Well, we often assume that epsilon here is distributed normally. We do normal distribution later in this lecture, using some mean and some variance, but here we can say 0, 1 just for the sake of concreteness. That's a continuous distribution, so we assume that the errors are normally distributed, which helps us do a whole bunch of statistics that we couldn't otherwise do so easily. As we'll see in a few modules, there's reasons why we do this, but this is a continuous distribution and is essential for any kind of statistical inference that we're going to do. Other continuous distributions include the logistic distribution, which also pops up a bunch when we're doing statistics, particularly of dichotomous type choice. So these things are very central for doing stats. You see there's a bunch of statistics. In terms of data generating processes, some stuff also comes up that's continuous. So for instance, timing. If you're trying to understand the length of peace before a war initiation, or before a civil war, or we're trying to find bargaining delay over time, the length of bargaining delay in government formation or in passing bills, right? These are delays. Delays are time, which is generally thought of as continuous. So that those kind of temporal issues are clearly time-related. If we have some kind of area-related thing, some kind of spatial thing, that could also be continuous in scope. So we assume that the process generating the data is continuous, and we treat the random variable as being described by a continuous distribution function. So that comes up a bunch. Finally, in game theory, a lot of distributions are naturally continuous. Sometimes you might think of, for instance, types as being dichotomous, so you're a good type or a bad type. But sometimes your type represents the information you got from some signal, and it could range from, say, 0 and the belief that the person, you're at a trial, and the 0 means you thought you absolutely sure after the trial that the person is guilty, and a 1 means you're absolutely sure after the trial that the person is innocent. But in between is a range of things which you're not quite sure exactly of innocence or guilt, so you have less clear beliefs. That would be a continuous distribution of possible types you could be. The state of the world could be continuous. Good economy, bad economy is an example used before, but maybe the economy is represented by some continuous value corresponding to expected GDP. You form beliefs about expected GDP. Those beliefs are continuous and represented by continuous distribution. You have some continuous distribution over all the possible GDP values. That continuous distribution comprises your prior beliefs, and this has to be represented by a continuous distribution function. Lotteries can be continuous. The case we did before of a discrete lottery, when you win 0 or some large amount, is discrete, but maybe it's just a continuous number that pops up between 0 and 100, how much money you win, it's some windfall thing from a random number generator. I don't know. There are lots of scenarios in which the actual lottery itself is continuous, treating the lottery not as an actual real-life lottery, but as a random process that produces some value. So that's usually represented also by continuous random variable, and we'll do examples of that shortly, of expected utility using continuous random variables, continuous distribution functions. So you see this comes up a lot. So even though this does require a little more technical stuff, right? It requires integration, requires some calculus. It will end up being really useful for social sciences, social science research, so it's important to go through now. But again, one last time, if you haven't gone through calculus before, either in this course or in some prior course, definitely go through that before you continue on in this lecture. As you can see from just this module, there will be integrals that we will have to go through and do, and I'm going to assume that you know how to do those, or at the very least understand the concepts behind them, and if you don't, it's going to be very confusing. Thank you very much.